All right, welcome back. So at long last, I want to talk about starting to compute the homotopy groups of spheres. So in this video, we'll compute pi1 stable, the first stable homotopy group. So the claim is that pi1 stable is just z mod 2. Okay, and that's got a non-trivial element. And we should actually recognize that it's going to be the suspension of eta, where eta is the Hopf map, from S3 to S2. And then for the suspension, I just suspend in both the source and target. And so I get a map from S4 to S3, not that you can read that. All right, so let me remind you of the Freudenthal suspension theorem, which I'm assuming that you know, and if not, you should go look in Hatcher. So this says that if X is an n-1 connected CW complex, then we can look at the suspension map on homotopy groups. So we look at pi I of X, suspend in the source and the target, and get a map to pi I plus 1 of the suspension of X. Struggling with my handwriting today. Okay, and I'll just call that map suspension by abuse. And what is the claim? It's that this is an isomorphism in certain degrees. So when I is less than 2n minus 1, and the map is surjective when I is equal to 2n minus 1. Okay, and then the important corollary is when we take X to be the n sphere, which of course is n minus 1 connected, and we can look at pi n plus I of Sn. Notice I've changed my indexing here, as is the convention, though it can be confusing. That maps to pi n plus I plus 1 of Sn plus 1. And this is an isomorphism. Well, I guess now it's for n plus I less than 2n minus 1. And so if I plus 1 is less than n, just subtracting the n from both sides, moving the 1 over. Okay, and so that tells us that by taking some, if we fix some I that we're interested in, we can take n large enough that we're in this stable range. So this is an iso for large n. And once we get to this isomorphism, we call this the stable range. Okay, and then that stable value is our stable stem. So we write pi I stable, though there are many notations for this that you'll see. This one's at least common. This is just pi n plus I of Sn for, let's see, I guess we need n greater than I plus 1. And this is what we call the I stem. I really can't write today. All right, bear with me. Sorry about that. Okay, if you prefer, you could think of this as the colimit over n of pi n plus I of Sn. And this is roughly how we define homotopy groups of spectra. So this is saying that this is the ith homotopy group of the sphere spectrum. And I know some of you are familiar with that and some are not, so don't worry too much about it. So let's look at the case that we're interested in. What are we taking the colimit over? So we've got pi 1 of S naught. We suspend and we get pi 2 of S1 maps to pi 3 of S2. And then we're looking at 4 spheres going to S3, pi 5 of S4, and so on. Okay, and of course, well, let's check our indices first, maybe. So be careful that this, if I look here at pi 4 of S3, that's really 3 plus 1. So my I is 1 here. And I guess 3 is greater than 1 plus 1, which is 2. And so at this stage, I do have an isomorphism. And then my n is only greater here, so my I is still 1. Really, I is just the difference between the index and the sphere dimension. Okay, so I is still 1, but my sphere is even larger, so I'm well into the stable range, and this is an isomorphism forevermore. And from our Freudenthal suspension theorem, we know that the previous spot is the surjection. Okay, so let's start filling in some values. Pi 1 of S naught is, of course, 0. Pi 2 of S1 is 0. Remember, S1 is a KZ1 space. Then pi 3 of S2 is a copy of the integers generated by the Hopf map, right? And this must surject onto pi 4 of S3. And so the claim here is that this is Z mod 2. And then once that's true, which we'll learn in this video, then it's Z mod 2 forevermore. Okay, and so then our colimit is pi 1 stable, and we learn that it's Z mod 2. Okay, so the point of all of this is that we can compute pi 4 of S3, this unstable homotopy group, and because we're already in the stable range, then this will compute for us that first stable stem. Okay, so that's what we'll compute. Before we do that, let me remind you of a couple facts from Hatcher, which you may or may not have seen. Sorry. I don't think these are due to Hatcher, I just mean that you can find them in Hatcher. So the first is, they're definitely not due to Hatcher, especially this first one. Okay, so the first is that you take any map between spaces, F from A to B, and this can be converted to a fibration. Okay, actually this is true in any model category. So if you're familiar with model categories, there's not much to say here. You can put a model structure on topological spaces. All I'm saying is that any map should factor as a fibration followed by a cofibration. And so what I do here is I take some fattening up of A, and I can even make this an acyclic cofibration, and that converts this to this map F tilde, which will be a fibration. This is just the fibrant replacement. Okay, we don't really need all of the higher power of model categories in this particular case. So if that's not familiar to you, let me just say in topological spaces, what does this look like? Well, I'm going to fatten up my, what should be my total space. So EF is going to be pairs A gamma that live in A cross paths on B. And then I want these to be paths that start at F of A. Okay, and then there's a map to B. This is what I'll call my F tilde. This is going to be my fibration. And that map is just evaluate at 1. But of course, these paths are contractible, so this total space is homotopy equivalent to A. All right, so we've just done sort of a fattening up of A, this fibrant replacement, and now we have a fibration. Maybe let me write that. Okay, so that's one of the facts that we'll need about fibrations, and we're also going to need, well, maybe we could just get away with that one, but I'll put it in this language because I think this is a useful fact, which is that if you have some fibration, say F to E to B, and you get a map, you have some map to the base space, so F from X to B, this is a different F than the previous one, then you can take the pullback in topological spaces, and this is going to be a fibration. And even better, the fiber is essentially preserved. So what do I mean by that? The fiber will be homotopy equivalent to F. So of course here I'm assuming that I had a nice fibration with a nice fiber that I could describe over all points. And so I just look at the fiber over the base point. Maybe let me draw a diagram for what I'm saying. So I have my fibration, and I can take the pullback of this map F. Okay, and then I'm just claiming that we have a fibration here on the left with the same fiber. Okay, at long last, we are ready to start this computation. I don't know why I moved that off screen, sorry, but let's go ahead and get started. So remember, we're computing pi 4 of S3 because we said that's where we first see the stable range for the one stem. Okay, so to get started, I want to think about the homology of S3, in particular H3 of S3 in integral coefficients. Well, I guess I am actually writing cohomology, and so we have this theorem that cohomology is represented by Eilenberg-MacLane spaces. Usually write the coefficients first. Okay, so this is the same as maps from S3 to KZ3, and of course that's a copy of Z. So what I can do here is take some map, and let's not take any map, let's take the generator up to choice. Of course there's choice of homotopy, but also the plus or minus 1. If you don't like that sort of algebraic thing, we can think of this very topologically. So our KZN spaces we can form by starting with a sphere and then attaching higher dimensional cells to kill off all the higher homotopy. And in that sense, this is just the inclusion of the bottom cell. So, okay, that depends on choosing a model for KZ3, but that's fine. And then the Hurewicz theorem tells us that if we look at the induced map from homotopy to homology, well, that's going to be an isomorphism, okay? And so here in degree 3, pi 3 of S3 to H3 of S3, and the homology of S3 by the universal coefficient theorem is going to be the same as the cohomology of S3, right? This is 2 connected, and we just said that's the same as, oh, wow, I really cannot write today, pi 3 of KZ3. Okay, so this map F star is an isomorphism. And now let's take that F and convert F to a fibration. Notice that doesn't really change anything up to homotopy because our total space will have the same homotopy type. So I'm still going to write S3 to KZ3, but of course I'm now fattening this up and taking a fiber replacement of S3. And then we'll just call the fiber X. And this induces, whoops, sorry about that. This induces a Long-Zach sequence in homotopy. So let's go ahead and look at that. I know these are all easy computations, but somehow there's a lot of moving pieces here and it's easy to get lost. So I'm going to spell it all out really explicitly. Okay, so here's my Long-Zach sequence. In homotopy, I drop down to pi I of the fiber, pi I of the total space, to pi I of the base. And so on. Okay, and of course this is mostly 0. Right? I only get something interesting in degree 3, and so that's also mostly 0, and I mostly have an isomorphism here. And then the only interesting spot is when I look at pi 3 of S3 to pi 3 of KZ3. Oh, we just saw that F lower star is going to be an isomorphism. Whoa. And so then I'll have zeros on either side. So what we've learned, I guess, is that we know the homotopy of the fiber entirely. So let's collect that all up. Well, most of the time it's the same as the homotopy of S3. So that's true when I is greater than 3. But then, at that 3 spot, we're going to get 0 because of this isomorphism. Can't see where I'm pointing because of this isomorphism. And then also below that, we'll have 0 and so on. So, this is 0 for I less than or equal to 3. And this is a common technique, by the way, so we'll see this and we'll use this again. I want to say that we just peeled off the bottom homotopy group. So really we just took S3. We now have a new space that has the same homotopy except for that first interesting homotopy group. So we've peeled that one off, but essentially otherwise it looks like S3 in homotopy. Okay, so throwing my pencil here, sorry. X is, I guess you can't see that happening. I don't know if you heard it. All right, anyway, what I'm trying to say is X is 3 connected. Whenever I get to the bottom here, things get jumpy. Okay, X is 3 connected. And so again, I want to use that Hurwitz theorem. And that's going to tell me that at the next dimension, I've got this map from pi 4 of x to h4 of x with integral coefficients, of course, being lazy and not writing it. And that's an isomorphism. But that pi 4 of x, that's also pi 4 of S3, the thing that we're trying to compute. Okay, so let's compute h4 of x instead. Okay, well, we're going to compute h4 of x by the fourth homology by actually computing the fourth cohomology. So let me say how to get there. Now I want to use that other fibration fact from Hatcher. So I want to take this map F that we started with and say, oh, KZ3 actually fits into a fibration. Right, we've got the loop path fibration, so that the fiber is KZ2. Seen this one a lot. And now I can take the pullback, and this is supposed to be contractible. Okay, so I can take the pullback, and that fact told me that I should have the same fiber, KZ2. And this pullback is equivalent to our X that we started with. If you don't like that, you could say convert this map X to S3 that we had to a fibration. That was just our inclusion. But pick a particular inclusion, convert it to a fibration, and check using the long exact sequence and homotopy that the fiber is KZ2. Okay, either way. In any case, we've got this fibration, and this is what we want to use the Serre spectral sequence for. At long last, spectral sequences come in, so we'll have KZ2 to our space X, something homotopy equivalent to it anyway, to S3. And we're going to do the cohomology spectral sequence. And why is that? We want this fourth homology. Why not start with the homology? Well, I'm working with the integral coefficients, and so I don't have that algebra structure. So the advantage of using the cohomological spectral sequence is that I can use the algebra structure. And then we'll just use the universal coefficient theorem to jump back to homology. Okay, so now this is our plan to use the Serre spectral sequence for, for this fibration. So standard setup, I've got my E2 page. I'm going to draw the cohomology of the base and the cohomology of the fiber. And the great thing about that is that I'll have the tensor product here. All of this should cook up the cohomology of the total space, which is our X. And that's the thing that we're after now. Okay, and, oh, I wrote all that, but I forgot to, I think you all know this by now, but maybe let me write that E2, oops, let's move all of this, because I think I'm going to be crowded for space. So E2PQ is HP of, well, it looks like our base now is S3 with coefficients in the cohomology of our fiber. And this should cook up the cohomology of the total space. Oh yeah, that's what I'd written here. Okay. And so I'm drawing this E2 page. And now let me get P and Q as usual. Let me label these indices since I think they'll end up being important for us. Okay, I'm not actually going to go up that far, but that's fine. Okay, and let's start this computation. So our cohomology of our base, of course, that's the cohomology of S3, nice and simple. And the cohomology of our fiber, that's the cohomology of KZ2, which I suppose we knew a while ago, right? We computed this using the spectral sequence long ago, but ultimately we'll push this computation further and we'll look in higher dimensions. And so it will be good that we've computed the cohomology of these Eilenberg-MacLane spaces. Okay, but so what do we have? We actually know this one in integral coefficients. So we've got Z, I'll call it 1, and let's just call the generator here X. We could call it iota 2 if you want, but it takes longer to write. There's X squared. There's a copy of the integers on X cubed. Wow, I really cannot write today. Okay, anyway, that continues. I'm just gonna, well, let me keep going and put in the cohomology of the base. So let's just call that generator Y. Of course, Y squares to be 0 because the cohomology of sphere is only interesting in degree 3. And what I was about to say is I just want to leave everything that's 0 is blank, right? So really I have 0 here and here and here and all over, and let me not write them all. But I do have some non-zero places. In particular, maybe let me point out, scrolling back up a bit, that so far we've mostly used the spectral sequence to figure out the cohomology of the base from the cohomology of the fiber. But this time we are actually interested in the cohomology of the total space, right? That's the one that we don't know. So I actually know the cohomology of the fiber and the cohomology of the base. And so on the E2 page, I have this tensor product. And so here I've got Z, and I could call that generator X tensor Y. I'll just write XY. Here I've got X squared Y, X cubed Y, and now truly everything else that we can see here on this page is just 0. Okay, so I want to start this computation and figure out what we're converging to. I think you have to be careful the first time you do something where it's not the loop path vibration, because not everything should necessarily die. I've made that mistake before. But what do we know? We know that X is 3 connected. Remember, it had homotopy groups the same as S3, except we peeled off that bottom one. So pi 3 of X is 0, and the lower ones are 0 as well. And so I know that H2 of X is 0, and I know that H3 of X is 0. Okay, so there's nothing interesting going on there. But that means that when I look over in my spectral sequence, I've got this copy of the integers in degree 2 and something in degree 3. And notice I'm referring to the total degree, so it's a degree 0 plus 2, so 2, and 3 plus 0, so 3. All of those things have to die, or I'd end up with something in the cohomology of X. So there must be a D3 differential. This one's actually tau, since it goes from edge to edge, and it should be an isomorphism. Okay, so we just learned that D3 of X has to be Y, and we could call that tau if we want. It's not going to help us this time. I'm not going to use the Steenrod algebra. I don't even need it here, though we will in later computations. But I am going to use that this is a spectral sequence of algebras. So d3 of x squared is, by my Leibniz rule, 2x d3 of x. And so that's 2xy. Now, again, a lot of our computations for a while have been in mod 2 coefficients, but we're not in mod 2 coefficients. We're talking about integral coefficients here. So, whoa, sorry about that. We just learned that this d3 is the times 2 map. Okay, I'm just putting it in a different color to be clear that it's not an isomorphism. I guess actually we could probably easily find out that this is the times 3 map in the usual way. Just continuing this computation, but I don't even need that. So what's the upshot? When we take cohomology of this E2 page to get to the E3 page, then, okay, this stuff will kill each other. And here I'll have a Z mod 2. So let's write that down. Okay, and now I'm basically done, so let me be kind of lazy. I had that copy of Z, and I've got this Z mod 2. This is in degree 3, 2. Okay, and so the total degree is 5. And then there's other stuff. We could have worked it out, but I don't care. That stuff is all in higher degree, is what I mean, so I don't care about it right now. So I'm going to learn that h4 of x is 0, and h5 of x, well, normally I might have to deal with some extension problems, but there's no extension problems here. It's just a single group, Z mod 2, so no extension problems this time. And I'm even getting away with not even worrying about which way my filtration of the, which way, right, really this E infinity page will converge to an associated graded for some filtration of this thing, and I don't even have to worry about that. I guess I should have said, though, that this is going to persist to the E infinity page, that Z mod 2. So notice that there's nothing else that can hit it up there, and there's nothing over here. So it does persist to the E infinity page. Okay, great. So now we know something about the cohomology of this space X. What we really want is the homology. We were after h lower 4 of x in integral coefficients, and by the universal coefficient theorem, we get that that's Z mod 2, right? We hom from this h lower 4 of x to z, and we must have gotten 0, so okay, we knew it was torsion, but then we also see this torsion bump down from that x term. Okay, so this is by our universal coefficient theorem, and that was the thing that we were after, because pi 4 of S3 was isomorphic to h4 of x. And so we've just learned that it's Z mod 2. And we were in the stable range, so that tells us that pi 1 stable is indeed Z mod 2. And it was being surjected by that group generated by the Hopf map, so we might as well say that it's generated by the Hopf map, and that concludes the proof. Okay, so we finally know our first non-trivial stable homotopy group for the stable homotopy groups of spheres, and the sort of next main goal is to push this kind of computation further. And essentially the method is very similar. We peel off some bottom homotopy group, we run this air spectral sequence on the appropriate thing, only of course the higher you go, the more chasing you have to do, and the more complicated the answer, but we'll at least be able to compute the first few stable homotopy groups in a similar way. All right, so let me stop this video there.